Hey, sixth grade. Today we will be covering lesson 710, Investigating Change. You'll be using diagrams, formulas, and graphs to make predictions and draw conclusions. Today you'll know you've got it when you can successfully make a graph to represent the information you've calculated in a table. We will start with our mental math and fluency today. I'm going to have you mentally record products, so you might want to have a post-it note or a whiteboard handy to record the products that you get after you evaluate these problems. Might be a good time to pause the video to go find those materials. You'll notice that we're going to have some exponents in these problems that we're going to be evaluating. So just a reminder, our order of operations are over here, GE, mod, SORA. We're not going to have any grouping symbols, but we will have exponents. You want to be sure that you evaluate the exponent before you go ahead and multiply by the value that's in the front, okay, or by the factor. The first one I would like you to take care of is 4 times 10 cubed. Good time to pause the video, see what you get, and then come back and check your answer. Welcome back. So if you did the 10 cubed, you should have gotten 1,000, and 1,000 times 4 will give you 4,000. The next problem I'd like you to try is 2 times 4 squared. Good time to pause the video and come back when you have a response. Welcome back. So 4 squared tells you that you need to multiply 4 by itself twice. 4 times 4 gives you 16, and 16 times 2 gives you 32. The next one I would like you to try is 7 times 3 squared. Go ahead and pause the video. Welcome back. So 3 times 3, or 3 squared, remember that exponent tells you how many times to multiply the base by itself. 3 times 3 gives you 9, and 9 times 7 should have given you 63. So at this time, I'd like you to take out your Everyday Math Volume 2 journal and open up to page 339 for today's math message. So on page 339, you'll notice that we have an image on the right that shows a ball being dropped. I'm going to read the journal page to you, and then I'll give you some time to work on this on your own. So it says the picture at the right was created based on a series of photographs taken at intervals of 1/20th of a second. You'll notice we have a table that gives us a lap time in seconds, and you'll notice we go from 1/20th to 2/20th, 3/20th, so each time we're progressing to 1/20th of a second. Next to that, you'll notice the total distance that the ball has fallen in that interval. So we start with 400ths, and then that doubles to 1600ths, and then that triples to 3600ths, so on and so forth throughout the table. The first question they're asking of you is how far did the ball fall during the first 1/4 second? So you'll need to think of an equivalent fraction to 1/4, but our denominator needs to be in 20ths. So 1/4 is equal to how many 20ths in order to answer that question correctly? Number 2, how far had it fallen after a 1/2 of a second? So you'll need to think of an equivalent fraction to 1/2, but our denominator needs to be 20ths this time. So 1/2 is equal to how many 20ths? Number 3A asks you to check the statement that you believe is true. Is it A, a ball falls at a constant or even speed? Or, as a ball falls, it picks up speed? So take a look at the picture over here, and I want you to pay attention to, as the ball falls every 20th of a second, what happens to the distance that it's covering, or you could even just look over here at the gaps in the amount of space in between each of those intervals. Okay. B is then asking you to explain your choice in problem 3A. A great time to now pause the video, give yourself maybe 2-3 minutes to see what you can do with this page, and then unpause the video and we'll go over the correct response. Welcome back. So if we look here, we'll see that 1/4 is equal to 5/20ths. So if we take a look in the table and we move down here to 5/20ths, we'll notice that that is equivalent to 1 foot of that total fallen distance. If we look at the 1/2 of a second, that's equivalent to 10/20ths. So if we follow that along on our table, we'll see that 10/20ths is equivalent to 4 feet of that fallen distance. You can also look over here. If I count 1, 2, 3, 4, 5/20ths of a second, I'm there at 1 foot. And if I count down the 10/20ths, or the 10 intervals of that 1/20th of a second, you'll notice the ball is equal to have fallen 4 feet. 3, check the statement that you believe is true. As you notice, the ball, as it falls, it picks up speed. It's covering more distance, so it's going a longer amount of space in the same amount of time. B, and the sample answer here would be the distance traveled gets longer from 400ths to 7600ths feet for the same time period. So the time is kept the same, but the distance that it's covering is longer, therefore it's picking up speed, it's getting faster. What I would like you to do now is have your journal, or just turn the page to 340. I'm going to pause the video here, or the recording of the video here, and actually show you something along with that page. On page 340, you'll notice our topic is what happens when an object is dropped. I'm going to read that page to you, and then I'm actually going to show you a video about some of the content in there. So it says that Galileo was an Italian physicist who lived from 1564 to 1642. His work led to the following rule for the distance traveled by a freely falling object. Distance traveled in feet equals 16 times the square of the elapsed time in seconds. Written as a formula, the rule is d for distance equals 16 times time, or d equals 16 times t squared, where d is the distance traveled by the object in feet and t is the time in seconds that has elapsed since the object started falling. For example, after 1 second, an object will have traveled 16 feet, or 16 times 1 times 1. After 2 seconds, it will have traveled 64 feet, 16 times 2 times 2. Galileo's formula really only applies in a vacuum. So a vacuum is an enclosed space from which matter, especially air, has been removed so that matter or gas remaining exerts less pressure than the atmosphere. I'd like to take this opportunity to show you a quick video from YouTube that gives you a real-world example of what an object falling in, regular airspace opposed to actually falling in a vacuum. So the video I'm going to show you shows two situations. First, we're going to be dropping a bowling ball, and a feather in a normal room. So there's air in the room, and the pressure is going to interact with the ball and the feather, obviously in different ways. I'm sure you've seen a feather fall from the sky before, and also a bowling ball. Hopefully not on your foot. The second part of the video is going to show you a different situation where the air pressure and the gases have been removed from this room. So you'll see that the ball and the feather are going to drop in a different way.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
So you'll see the feather floats. This is without the air in the room. So this looks a little different. You'll notice they're both falling at the same speed. There's nothing interacting with that feather to make it float. So they're going to fall in the same amount of time. So now with that new understanding of what an object falling in a vacuum actually looks like, let's go back to our page. So it says, however, it is a good approximation for the fall of a dense object such as a bowling ball over a fairly short distance. So for number one, what we're going to have you do is the following table shows the approximate distance traveled by a freely falling object at 1 second intervals. Use Galileo's formula to complete the table. So you'll see that they've started this for you. Obviously in 0 seconds, it's going to fall 0 feet. In 1 second, we're going to take that 16 times the time squared. So 16 times 1 to get 16. For 2 seconds, we're going to do 16 times 2 squared, or 16 times 2 times 2. For 3 seconds, we're going to do 16 times 3 squared, or 16 times 3 times 3. I would like you to complete the rest of this table using that formula of 16 times the time squared with 4 seconds, 5 seconds, 6 seconds, 7 seconds, 8 seconds, and 9 seconds. Okay, so this is a good time to pause the video, see what you can get from that, and then come back to check your answers in a moment. Welcome back. So if you've done that correctly, okay, these are the values that you should have. So for 4 seconds, it should have traveled 256 feet. 5 seconds, 400 feet. 6 seconds, 576 feet, 7 seconds, 784 feet, 8 seconds, 1,024 feet, and 9 seconds, 1,296 feet. You'll notice number 2 asks you to graph the data from the table above onto the grid on journal page 341. So on the next page, you'll notice that there has been a graph that's started for you. So from here, we'd like you to continue to plot those points for 4, 5, 6, 7, 8, and 9 seconds. And then you're going to come back to this page, and we'd like you to answer the question about using the graph to estimate the number of seconds it takes an object to fall 500 feet, ignoring the air resistance. So with your graph, you're going to take your finger, and at 500 feet, you're going to follow it along to your graph and see where that distance intersects with an amount of time. So at what second will we notice that the bowling ball has traveled 500 feet? So again, a good time to pause the video now and then check back in once your graph is complete. Welcome back. This is what your graph should look like. You'll notice we don't have a straight line today. We have a curve. And that's because we have exponential growth, which means that within each of those 1/20th of a second, our distance traveled gets longer. So therefore, our graph will curve upwards. So back to that question at 500 feet about how long will it take for the ball to reach that point. If you follow your finger along that line of 500 feet, and then you follow it down to your x-axis, you'll notice each of these, we have 5 lines between each of those holes. So at about this point here, we should notice that it takes about 5 6/10 seconds for the bowling ball to travel that far. Okay? You're going to submit page 342 to us today to show that you've understood today's lesson about investigating change. We have created some slides for you to complete this a little bit easier than taking those pictures and us squinting our older eyes, no offense, Mr. Zerga, to try to see what you have written there with your pencil. So the first slide just lays out the directions for the page. I'm going to go over that with you. So if you're on page 342, you can follow along with me. It said the speed of a freely falling object increases the longer it continues to fall. You can calculate the speed of a falling object at any given instant by using this rule. Speed in feet per second equals 32 times the elapsed time in seconds. So we're no longer dealing with exponents. Make a prediction right now. What's our graph going to look like? All right, if we're just simply multiplying by 32, how will that look different than when we were multiplying by an exponent? Or you can use this formula, S for speed equals 32 times T, T meaning time, or T representing time. In the formula, S is the speed of the object in feet per second, and T is the elapsed time in seconds since the object started falling. For example, after 1 second, the object is traveling at a speed of about 32 feet per second, 32 times 1. After 2 seconds, it's traveling at a speed of about 64 feet per second. 32 times 2. The next slide that's been created for you, you'll see that we've taken the formula from the previous page and placed it here for your convenience. And then for number 5, we're asking you to complete the table, graph the values from the table, and draw a line through the values to show the general pattern as time passes. So I've placed text boxes here for you, so you just need to type in what you get after you do 3 times 32, 4 times 32, 5 times 32, and 6 times 32. Then I'm going to ask you to come up here and insert a line. So you're just going to hit select line, choose a line, and you're going to continue that line with the values that you've gotten from your graph over here. Okay? From here, you'll notice slide 3 has some questions that we'd like you to respond to. Oh, wait, I'm still creating a line here. We don't want to do that. So it says the text boxes have been inserted for you again. So all you need to do is click here to answer the questions, what the questions are asking. Number 6, at about what speed would an object be traveling 18 seconds after it started falling? So all you need to do is come over here and take 18 and multiply it by 32. Your rule is X, or 32X equals Y. So multiply by 32. If a freely falling object is traveling at a speed of 290 feet per second, about how long has it been falling? So now you're going to work backwards. If I take the 290 and I divide it by 32, what do I get? That'll tell you how long the object has been falling in a number of seconds. Can't wait to see what you guys come up with. I only have 2 seconds. Bye!